In this video, we're going to continue learning our rules for naming ionic compounds and making formulas for ionic compounds. The only thing is this time we're going to take a look at ionic compounds that contain polyatomic ions. So what we learned so far is that an ionic compound was a compound that contained a metal and a non-metal. And specifically those were binary ionic compounds. Now we're going to talk about an ionic compound called a ternary ionic compound. And that's basically just an ionic compound that's composed of more than two different elements. But the thing is, there has to be a polyatomic ion in there. So it's usually one metal and the polyatomic ion. There are some exceptions, but as soon as you see that polyatomic ion, you know you're still dealing with an ionic compound. Okay, so ternary compound, ternary meaning basically more than two, let's say three, for example. So you might have something like Na, NO3. There's more than two different elements there. There's sodium, nitrogen, and oxygen. And this NO3 here, that's actually a polyatomic ion known as nitrate. So that's how I know this is an ionic compound. The bond within the ionic compound between the sodium and the nitrate is an ionic bond. The nitrate is negative, the sodium is positive, and they attract. So what we're going to be doing here is we're going to be taking a look at how to name ionic compounds that contain a polyatomic ion and write formulas for ionic compounds that contain polyatomic ions. This is another example of a polyatomic ion over here, CO3 2-. It looks like a compound, but it's not. It's just a group of atoms together, so polyatomic meaning many atoms together, ion that have a charge. Okay. If it was a compound, the overall charge has to be 0. You know that in a compound, the overall charge is 0, but because there's a charge here, we know that the CO3 2- is not a compound, but rather an ion, and specifically we call it a polyatomic ion. So groups of atoms connected together with an overall charge. This here is a table that shows you all the different types of polyatomic ions that exist. You'll notice that the majority of them have a charge of have a negative charge. So -3s, -2s, -1. There is one that has a positive charge. That's called ammonium. Okay. You are responsible for knowing the ones that are bolded. Some very important ones that you want to focus on are things like phosphate, phosphite, hypophosphite. And these ones are pretty easy to remember. If you remember phosphate is PO4, then you just go down. So phosphite would be PO3, hypophosphite, hypo meaning below, so below phosphite is PO2, and they all have 3-. Over here you might see hydrogen phosphite, so it's similar to phosphite, but with an H in front and a 2-. Carbonate is very important to know. Sulfate is very important to know, and if you know sulfate, ite is just below in terms of the number of oxygens, so it's SO3 2-. That would be good to know as well. Hydrogen carbonate, very similar to carbonate, just with a hydrogen, and you'll notice that there's a little minus as opposed to a 2-. So without the H, it's 2-. As soon as you add the H, it becomes minus. Nitrate is good to know, NO3-. And nitrite, again, look at the trend here with the oxygen. The ite is always one lower than the 8 in terms of the oxygen, but the charge stays the same between 8 and ite. You might need to know hydroxide, OH-. Iodate is IO3-, and then one below iodite is IO2-. And if you even go one below iodite, that would be hypoiodite, which is IO-. So you can remember little tricks like that to help you remember these compounds. We can take a look at chlorate. Chlorate is CO3-. If you say chlorite, the O, just take away one, that's ClO2-. So chlorate, was ClO3-, chlorite, ClO2-. Below chlorite, hypochlorite is ClO-. And there's even a little prefix for something above chlorate. Perchlorate would be ClO4. So usually the pair is one above the chlorate, the 8. Okay. Here's another polyatomic ion over here, cyanide. I know it's not bolded, but I just want to point that out. Whenever you're not sure of what a polyatomic ion is, what name you're looking at, what the formula is, you can always research it. So for example, you can research what this polyatomic ion is in this table. There are a few tricks you can use to memorize the polyatomic ions. Here's a neat video you can watch. It's a catchy tune of someone rapping the polyatomic ions. One trick is using the saying, Nick the camel had a clam for supper in Phoenix. And so the trick goes like this. If you look at the word Nick, the underlined letters represents the first element in the polyatomic ion. So for example, if I'm looking at Nick, the first element is going to be N. Then the vowels is going to be my valence, my charge, how many negatives there are basically. So there's one vowel, so it's going to be -1. But let's take a look how we figure out the oxygens. The number of oxygens would be the number of consonants. So anything that's not a vowel, so N, C, K, there's 3 O's that means. And because there's one vowel, it's a charge of -1. So the charge goes on top, the subscripts stay at the bottom. Let's try this one here, camel. C is the first letter identified. In terms of number of oxygens, that's our consonants, so 1 C, 1 M, 1 L, so there's 3 oxygens. And in terms of the charge, that's going to be 2- because there's 2 vowels. So you can use this little trick here to remember some of the most important polyatomic ions that we're going to be dealing with. Now, a quick little practice question for you to attempt. If you take a look at, let's say, Na plus and NH4 plus, why don't you think they would come together to form a compound? Think about the charges when you're answering this question over here. Okay, same idea with these ones here. Think about why you might not have Na plus and Cu plus form a compound with each other. So this again is our trick. Nick the camel ate a clam for supper in Phoenix. You can use this trick to memorize some of the most important ones that we'll be dealing with in grade 10. Nitrate, carbonate, chlorate, sulfate, and phosphate. And then from there you can remember others. So if you know nitrate is NO3 minus, you know nitrite with the ite ending, nitrite would be one below in terms of the oxygen. So it would be NO2 minus. I really don't recommend you sit there for hours and memorize every single one. What I recommend you do is you actually do practice problems with these polyatomic ions, and then you'll start to internalize them yourself. So don't waste your time just memorizing. Practice, and they'll eventually stick. If, again, you're not sure of a polyatomic ion in terms of what its formula is, you can always look it up. You'll see tons on Google. Just Google the name, and then you should see the formula as well. So let's take a look at how to name compounds that have polyatomic ions. Again, these are still considered ionic. Here we have a metal and a polyatomic ion. And so what you have to do is, we're going to start off with this example here, KNO3. First, you name the metal, so the one on the left. So we know that's potassium. Then you have to find the name of the polyatomic ion. So NO3 over here, if you go look in your table, you'd see that NO3 is actually NO3 minus. Sorry, this looks a bit misleading. The minus should be on top here. Same over here, should be on top here. The NO3 minus is actually nitrate. So you write that down. And you're not going to change the ending. You're going to write it as you see it, nitrate. Then you combine the two names. So you have potassium nitrate. You can try CaSO4. In this case, we have our metal is calcium. the SO4, if you looked in your table, you would notice it's SO4 2 minus. That's sulfate, so calcium sulfate. Not sulfite, that would be SO3 sulfate. So you're not even changing the ending, okay? Now don't confuse that with sulfide. Calcium sulfide would be this, CaS, because you change the ending of sulfur to sulfide, okay? Don't confuse that with sulfite either. Calcium sulfite would be this, because this polyatomic ion over here is sulfite, okay? So you have to pay close attention to the ending. You're not modifying the ending in polyatomic ions. You leave them as you see them. So do not change the ending. That's super important to remember. Here are some practice problems for you to attempt. You can use your tables to remember the names of the polyatomic ions in the meantime. So again, the general idea is you name the metal first. So for example, if we're doing this one over here, we would have magnesium, as a metal. If you go in your table of polyatomic ions, you'd see that OH minus is hydroxide. And then you combine the two names together. So you'd have magnesium hydroxide. So you should be able to attempt these ones here. Again, do not modify the ending of the name for polyatomic ions. Sometimes this can become a little bit more complicated. Sometimes the compound you're naming, the ternary compound you're naming, might have a multivalent element in it. And so again, we're using the stock system when we're naming multivalent elements. It's the same rules that we saw for multivalent for compounds with multivalent elements in them. It's just that you have to be very careful when you're determining which multivalent metal you have. Okay, so over here we have Cu2CO3, and so our goal is to figure out which copper we have. So typically I start off by writing out the name. So I would write out copper brackets carbonate, and I have to figure out which charge I have for copper. Is it copper 1 plus? Is it copper 2 plus? So I need to do the reverse crisscross. Don't assume it's 2 just because you see a 2 here. Again, it's not the number of coppers you're looking at, it's which ion it is. Okay? Now, when you do the reverse crisscross, you need to be careful here. You cannot change the polyatomic ion. You need to protect it. If you move that 3, you no longer have the polyatomic ion there. So you treat it as if it's one unit and you cannot change it. Okay? So here's what I do when I do a reverse crisscross. I have Cu2, and I'm going to put the polyatomic ion in brackets. CO3. And outside the bracket, I'm going to put a 1 to show there's only one CO3 here because it acts as one unit. I'm going to circle the 2, bring it on top over here. I'm going to circle the 1 over here and bring it on top. So that way the CO3 remained as CO3. If you circled the 3 and brought it up, you would have made a mistake. It would have been wrong because now you no longer have CO3 there. Polyatomic ions cannot be destroyed in the formulas here. So now we have Cu1 plus. We know it's plus because it's a metal. And then CO3 2 minus. You can check to make sure that this is the correct charge of carbonate, and it is. That means there was no reduction that happened. And we have copper 1 here. So we have copper 1. And our polyatomic ion is carbonate. You don't change the ending. So we have copper 1 carbonate. You could have also done this using the charge balancing method. So for example, I could have put copper, question mark, CO3, and you know the charge of carbonate is CO3. This is your checker ion here. You know the charge of carbonate is 2 minus. This is your checker ion here. You can check in the table and you would have memorized it by now. So over here, we know that the overall charge of the compound has to be 0. We only have 1 carbonate here, only 1 carbonate, and actually we have 2 Cus. So let's add another little Cu here. So over here we have -2, and we know the overall charge has to be 0. So what are the charges on the coppers here? If you said +2 and +2, you'd be wrong because that would be +4 minus 2, that's 2 plus. But if you said +1 and +1, then that would be +2 minus 2, 0. So you know that your coppers are copper 1s. Okay, so you never want to break apart this polyatomic ion or remove its subscripts. Always put it in a bracket to protect it when you're doing the reverse crisscross. Otherwise, you will make a mistake and you will destroy your polyatomic, and then you'll get the wrong charge for the multivalent element. So you can try this one here, naming CuCO3. I know you might think we just did it, but if you think about it, we didn't. The previous example was Cu2 CO3. This one is simply CuCO3. So I'm going to start with my first step. It's just naming the compound as I normally would. So I'd have copper. And I know copper is multivalent because I did a lot of practice and I can recognize that now. Brackets. Carbonate. Okay, and now what I'm going to do is I'm going to try to figure out which copper I'm dealing with. I'm not doing this example here. I'm doing this example over here. Okay, so you can do the reverse crisscross. I'll show you how to do that. So again, we have Cu. 1. Put your CO3 in brackets. And there's only 1 CO3 here, so we'll put the 1 on the outside. If there were 2 CO3s, you would have a 2 on the outside. Circle the 1, bring it up, and you get Cu plus 1, CO3 minus 1. Make sure this is an uppercase O here, not a lowercase o. And then you have to take a look in your table. Does this actually match the charge of carbonate? And you'll see it doesn't. Carbonate has to be -2, so that means it was, yes, right, you guessed it, it was reduced. So to get it back up to -2, you have to multiply by 2, everything by 2. That means the carbonate charge there, and also the copper charge there. And then that will give us Cu, 2 plus, or plus 2, CO3, 2 minus. That means we have copper 2 carbonate. Okay. You could have also done this using the charge balancing method. You have 1 copper and you're not sure what the charge is, so we'll put a little question mark here. We have carbonate, only 1 of them. And we know the charge of carbonate is -2. We know overall the charge of the compound has to be 0. So if this is -2 over here and we only have 1 copper, if you said it was copper plus 1, you'd be wrong because plus 1 minus 2 is -1. That's not right. So you'd have to say it's copper plus 2, which makes sense because plus 2 minus 2, that is 0. So it's copper 2 carbonate. And again, you don't change the ending of the polyatomic ion. So here are some practice problems to attempt. You should practice naming these compounds until you have had sufficient practice with them. Practice to reverse crisscross, the charge balancing method. If you're not sure of what the compound is, you need to, what the polyatomic ion is, you should look it up in the table that's provided to you in your notes. And you'll notice over here that I put 4 question marks next to this one here. I need you to think about why I put 4 question marks when you're naming it, okay? So you might want to ponder this. This will help you out a little bit. Why wouldn't you call it sodium 1 hydroxide? You would just call it sodium hydroxide, so think about that carefully. Now we're going to make formulas. So we're given a name, for example, aluminum nitrate, and we need to convert that into a formula. And you can use a crisscross method, or you can use your charge balancing method. It's similar rules. You just have to be careful with how you approach this. So your first step is going to be to write the ions side by side. Aluminum is in group 13, so it's going to lose 3 electrons. That's Al plus 3. Nitrate, if you go look at it in the polyatomic ion table, is NO3. And what I'm going to do is I'm going to put the polyatomic ion in brackets. I always do that to protect it. But its charge can remain outside the bracket because you need to make it available for crisscrossing. Okay? So leave the polyatomic ion itself, the atoms within it, in the brackets, but the charge can be outside the bracket on top, so it's available for crisscrossing. Circle the 1, bring it down to the side of aluminum here. Circle the 3, bring it down to the side of the nitrate over here. And so now we have Al. I'm not going to write 1 down because it's implied now. Keep the NO3 in brackets. NO3. Keep it in brackets. And the 3 there on the outside here. Okay. If you didn't have it in brackets, it would look something like this. Al NO33. That's no longer nitrate. That's nitrogen with 33 O's. That's not nitrate anymore. So that would be wrong. You want to make sure that you keep the polyatomic ion in brackets all the time, unless there's only one. And I'll show you an example of that later on. The other method you could have used was the charge balancing method. So this is our final answer here. Charge balancing method. Write down the charge of the ions side by side. So Al plus 3. And put this in brackets, NO3 minus 1. We know the overall charge has to be equal to 0. Right now we're not there yet. We have plus 3 minus 1, that's plus 2. I need to go down a bit more, so let me add some more negatives. I'm going to add another NO3 there with a minus 1. Plus 3 minus 1, that's still plus 1. That's not quite there yet. We still have to go down a little bit. So I'm going to add one more NO3 here. And it seems like this makes sense now. Now this overall is negative 3. This is positive 3. And now we have an overall charge of 0. To do that, we just needed 1 aluminum. And then brackets, NO3, three nitrates, just like that, aluminum nitrate. You get the same answer, just a little bit more logical with the charge balancing method. Okay, let's try this one here, copper to hydroxide. So you can use the charge balancing method, or you could use the crisscross method. So we'll try with crisscrossing first. So we have Cu plus 2. Again, put your polyatomic ion in brackets. Everything but the charge should be in brackets. Minus 1. So this is plus 2, not a 1 here. Then crisscross. Bring the 2 all the way to the bottom right of the bracket here, and the negative 1 all the way to the bottom of copper over here. So now we have Cu. I'm not going to write the 1 because we know that it's implied. OH, keep it in brackets. 2. I knew this was copper 2 plus because it told me copper 2 hydroxide. Okay. Just like in the other example, you could also do the charge balancing method. Cu plus 2. Put your OH in brackets. Remember, the overall charge has to be 0. Right now it's not there because plus 2 minus 1 is plus 1. So we need to go down a little bit more. Let's add another negative charge. So we'll add another hydroxide. And that gives us 0 now because we have plus 2 over here. Negative 2 over here. And that's an overall charge of 0. So we just needed 1 copper to do that. And 2 OHs. 2 hydroxide ions. So you should attempt these problems here. I'm going to walk you through these two. So try them out yourself first, and then afterwards check them against my solutions. So we'll start off with the sodium carbonate. So we'll do the crisscross method first. Na plus 1 because it's in group 1. Carbonate, let's put it in brackets, our CO3 in brackets. But our charge for carbonate we're going to leave outside of the bracket, minus 2. We'll crisscross, bring the 2 down here, bring the 1 down here. Now I'm going to have Na2 CO3 with a 1. Now because it's the 1 over here, I don't have to keep the brackets anymore. I can actually remove the brackets and the 1 because the 1's implied. So I can just rewrite it as Na2 CO3, just like that. For iron 3 nitrate, we have Fe plus 3, nitrate, put it in brackets except for the charge, which you leave outside of the brackets to make available for crisscrossing, minus 1. Grab this one, bring it down here, grab this one, bring it down here, and we get Fe NO3 brackets 3. Okay. Another one I want to attempt with you, just to show you an extra step you might have to take, is this calcium carbonate over here. So we're going to make the formula for calcium carbonate. We'll do that just up in this little area here. So we'll put the ions side by side. Ca plus 2, CO3, put it in brackets to protect the ion, minus 2, and then you're going to crisscross. And so we get Ca 2 brackets CO3 2. And so you'll notice that you'll actually have to reduce because you have 2 over here and 2 over here. You can reduce by dividing by 2. You're not going to divide any of the subscripts of the polyatomic ion itself. The CO3, that cannot change. Just what's outside the bracket can change. So when we reduce, we get Ca CO3. The reason there's no more bracket around there is because 2 divided by 2 is 1, so we have 1 carbonate. You could have done the charge balancing method as well, and it would have yielded the same results. You would have had Ca plus 2, CO3 minus 2, and it has to be equal to 0, and it already is equal to 0. Your plus 2 and your minus 2 cancel each other out, so you just needed 1 calcium and 1 carbonate to make that happen. Okay, so I do want you to attempt these. There is one that you may not know how to do. This ferrous over here, I accidentally put that in there. We did not learn the classical system. Ferrous is actually iron 2. We're using the stock system, not the classical system. So just fix that. Make sure it says iron 2, not ferrous. You can attempt this one on your own, and again, make sure you check your answers against mine. It's the one I did on a previous slide. Same with this one here. It's the one I did on the previous 2 slides. Make sure you try it on your own first, and then check my solution. You should, like I said, do these practice problems. Once again, fix the ferrous to iron 2, and that'll make things a little bit easier to comprehend. So again, this ferrous over here is iron 2 in the stock system. I'd like you to try to determine which polyatomic ion this is. Write its formula as you would see it in a formula for a compound, and tell me its name.